Okay, so what I want to do is start the second of our lectures now on the McCall one-sided labor search model. So in the first lecture, we essentially did the following. We set up the Bellman equations for an employed worker who is working at wage W, and we set up the Bellman equation for an unemployed worker who is currently going to receive an unemployment benefit and then take a draw from the exogenous wage distribution in the next period. That unemployed worker is going to accept the wage offer if the wage draw is greater than or equal to the so-called reservation wage, which we also characterized in the last class. And hopefully you guys remember that we derived an equation given by the following. W star is equal to B, the unemployment benefit, plus 1 over rho plus delta, that's the discount rate plus the separation rate, times the integral from the reservation wage, W star, to the highest possible wage, W bar, times 1 minus F of W, where F is the cumulative distribution function for the wage draws. And we called that last term A of W star. And what we did was we proved that there exists a unique reservation wage, W star, that is somewhere between 0 and W bar. And so the model does admit an equilibrium reservation wage. We also illustrated this reservation wage graphically. Let me just write or sketch that graph here really quickly, because I'm going to come back to this graph today when we are talking about a couple of the basic comparative static results of this model. So on the horizontal axis, we look at different possible values of the reservation wage, W star, and we know that it has to be somewhere between 0 and the upper bound on what the wage can be from the wage draw, W bar. The unemployment benefit is independent of the reservation wage. The left side of this equation up here is simply equal to the 45-degree line. And the right side of this equation, we showed using by evaluating capital A at a reservation wage of 0 and also capital A at a reservation wage of W bar, as well as taking the derivative of A with respect to W bar and evaluating it using Leibniz's rule, which is a little bit of a tricky formula because the thing we're differentiating with respect to is one of the limits of the integral. We showed that the right-hand side of this equation has the following shape to it. It is strictly decreasing and convex towards the origin, because the second derivative of A we showed was strictly positive, I believe. Yes, that's correct. So where the right-hand side of this equation intersects the left-hand side, or the 45-degree line, tells us exactly where our equilibrium reservation wage belongs. Okay, what I would like to do today is talk about how the reservation wage is affected by changes in some of the key exogenous parameters of the model. One of those parameters that I think is interesting is the unemployment benefit. This one is going to end up having a big effect on the reservation wage and will ultimately, therefore, have an effect on the amount of unemployment consistent with this model in the steady state. Let's first compute the comparative static mathematically, and then we will illustrate the same result graphically to provide a bit of intuition. So how do we compute then the derivative, the partial derivative of W star with respect to B? Remember, the implicit function theorem here basically says that the reservation wage is going to be a function of the unemployment benefit, the discount rate, the separation rate, as well as the variables that characterize the distribution of wages. So W bar and capital F. If we were to take the derivative of this equation with respect to B and solve for dW star dB, here's what it would look like. So the left-hand side would be the partial of W star with respect to B. The right-hand side has a B appearing in two places. The first term, which is the intercept term, but B is also inside, or W star, I should say, is a function of B. So it would be 1 plus the derivative of this whole term A with respect to W star times the partial of W star with respect to B. We have to apply the chain rule. Now, fortunately, we know what the derivative of A is with respect to W star. We evaluated that in the last class. So if we group terms here, that's going to be 1 plus A prime is this -1 over rho plus delta times 1 minus F of W star. So we swing that to the other side. We get 1 plus 1 over rho plus delta times 1 minus F of W star. That whole quantity times dW star dB is going to be equal to 1. Therefore, the comparative static dW star dB will be equal to, if I multiply both sides by rho plus delta and then divide by rho plus delta plus 1 minus F of W star. This is the result I get. And you will notice that it is a positive over a positive plus a 1 minus F is also a 1 minus a probability, so that's also positive. Moreover, hopefully you see here that it's something divided by something plus something positive. Right, and the rho plus deltas are identical on the numerator and the denominator, which means that this comparative static has to be a positive fraction. So increasing the unemployment benefit by, let's say, $1 is going to increase the reservation wage, but by less than $1. So the reservation wage rises, but less than 1 for 1 with an increase in the unemployment benefit. Now, intuitively, why does this result make sense? Well, as the unemployment benefit goes up, the cost of searching for a new job while unemployed effectively goes down, right? Unemployment is no longer as painful because the unemployment benefit is higher. And so what searching workers are going to do in that case is hold out for a higher reservation wage, okay? So higher unemployment benefits are going to raise the minimum wage that unemployed workers are going to be willing to accept to actually take a job. Now, can we illustrate this comparative static graphically? Well, we should be able to do that. And hopefully you see exactly what is going to happen here. Remember, this line here is independent of the reservation wage. It's just a horizontal line at the value of, let's say, some B1. And where the right-hand side of this equation intersects the vertical axis here occurs at B1 plus A of 0. So you see here that by raising the unemployment benefit, it basically shifts both of these lines vertically by the same amount. And as a result, you can see that the new intersection point between the right-hand side, this b plus a of w star term, and the left-hand side, w star, which does not change, is going to result in a higher equilibrium reservation wage. We'll call it w star 2. So this comparative static can be computed quite easily by using the implicit function theorem, and it can also be analyzed graphically by using our graphical framework here that we developed in the last class. Okay, let me now move on to the second comparative static result. And in fact, what I want to do now is evaluate how the reservation wage changes with respect to the discount rate and the separation rate simultaneously. The reason why I can do this is hopefully you guys see from this equation that characterizes W star that rho and delta both enter the right-hand side in exactly the same way. And so the comparative static, the actual derivative that we're going to find for each one of them is going to be identical. So however the discount rate affects W star, it's going to affect it the same way that the separation rate does. Now the intuition for the effects is somewhat different, and we'll talk about that, but the comparative static is exactly the same. All right, let's evaluate that comparative static. So the left-hand side becomes dW star, let's say with respect to the discount rate, okay? That's going to be equal to the derivative of the right-hand side with respect to the discount rate, which appears in this term as well as in the limit through W star. So this would be, let's see, -1 over rho plus delta squared times the integral from W star to W bar, or 1 minus f of W dW, minus 1 over rho plus delta times 1 minus f of W star times dW star d rho. In other words, the second term here is exactly equal to A prime times dW star d rho, exactly like we did in the first comparative static. So effectively, we have to use a product rule here. Okay, we can manipulate this expression quite easily. Let's multiply both sides of this equation by rho plus delta, and then collect terms. So it would be rho plus delta plus 1 minus f of W star. All of that times, let's see, dW star d rho would be equal to -1 over rho plus delta. Remember, we're multiplying both sides here by a rho plus delta, so one of these cancels, times the integral from the reservation wage to W bar of 1 minus f of W dW. And then if we divide both sides by this term here, rho plus delta plus 1 minus f of W star, you're going to find that the partial derivative of W star with respect to rho, which by the way will be equal to the partial derivative of W star with respect to the separation rate. Okay, the comparative statics will be identical for reasons discussed just a minute ago, is -1 divided by rho plus delta times rho plus delta plus 1 minus f W star times the integral from W star to W bar of 1 minus f of W dW. Now, what is the sign of this comparative static? It's a negative divided by a positive times a positive plus a positive. So that's a negative times an integral of 1 minus f of w. That's 1 minus a probability. So that's a positive. So it's a negative times a positive makes it a negative. So increasing the discount rate, or alternatively, increasing the separation rate, is going to lower the reservation wage. Now, let's think about the intuition for this result. As the discount rate goes up, agents are going to discount future payoffs, future consumption levels at a higher rate. They are more impatient. They value the future higher than they do, they value the present higher than they do the future. So in some sense then, agents that are unemployed are going to be less willing to kind of wait around for a better wage offer in the future. If they're becoming more impatient, they're going to be more willing to accept a slightly less desirable reservation wage. Okay, so higher discount rates means that agents put a premium on the near term. And so unemployed workers are going to lower their reservation wage. They want to get back into work as quickly as possible. Now, how does this show up graphically? Forget the dashed lines here. That was the comparative static with respect to the unemployment benefit. If the discount rate or the separation rate increase, what happens to the right-hand side of this equation that characterizes W star? As rho or delta gets bigger, the entire A term is going to shrink. And therefore, this line here is going to kind of rotate down in a counterclockwise fashion. In which case, the new equilibrium point would be over here to the left, let's say at W3 star. So in the case of an increase in the unemployment benefit, the right-hand side, this B plus A of W star term shifts up, as well as the horizontal line evaluated at B shifts up by the same amount. But if rho or delta increase, then this A of W star term is going to rotate counterclockwise down a little bit, therefore reducing the equilibrium or the new reservation wage. Now, we talked about the intuition for why higher discount rates should lower the reservation wage. Let me just briefly mention here some reasons why a higher separation rate would tend to lower the reservation wage, because I think the intuition is slightly different. I think the best way to explain this is to think about how a higher a higher separation rate. So what happens when delta gets bigger? How that affects the gap between the value of having a job and the value of being unemployed. Okay, what I'm going to argue is that a higher separation rate basically shrinks the premium that one obtains by having a lifetime utility associated with having a job relative to what your lifetime utility would be if you were an unemployed worker. All right, now recall that the value function for a worker working at wage W, we talked about this in the last lecture, was W plus delta times VU, which is the value function of an unemployed worker, divided by rho plus delta. The value function for an unemployed worker can be written as the reservation wage divided by the discount rate, rho. Both of those were derived in the last class. What is the gap between these two value functions? In other words, what is the premium that one would expect to earn over one's lifetime relative to unemployment? Well, it would be W plus delta times VU, which is W star divided by rho plus delta minus W star divided by rho. Well, that's equal to, let me separate the terms here, W divided by rho plus delta plus quantity delta over rho plus delta minus 1 times W star over rho. That is equal to the real wage over rho plus delta plus, let's see, delta minus rho minus delta over rho plus delta times the reservation wage over rho, which is just equal to the difference between the wage and the reservation wage divided by rho plus delta, which of course is a positive number, since if you are employed and working, presumably your wage is going to exceed whatever your reservation wage is. Now, the point here that I want to illustrate is that if the separation rate were to suddenly get larger, if instead of workers being separated from their jobs at, let's say, a 5% rate, if that now is at a 10% rate, so there's a 10% chance that an employed worker loses his or her job in any given period, then what happens to this premium of the value of being employed relative to the value of being unemployed, right? It's going to go down. As delta gets bigger, the gap between the value function of an employed and an unemployed person goes down for a given reservation wage, assuming that that is constant. Okay. Now, why is this happening? This occurs because the expected lifetime utility of a job is going to be lower. If you know that you are going to lose your job now at a higher likelihood than you used to, then the expected value of any future job is automatically going to be lower. And what I would say is that the effect of basically all jobs being less attractive moving forward is that an unemployed worker who is searching for a job is in some sense going to be less picky about that particular job that he or she chooses. And so the reservation wage will fall. Unemployed workers will be willing to accept more jobs if they know that any job they could possibly have is going to be worth less in the future because the separation rate is now higher. So the intuition there is slightly different than it is for an increase in the discount rate, but the magnitude of the comparative static is exactly the same. A higher discount rate makes agents more impatient, and therefore unemployed workers are willing to accept lower reservation wage. A higher separation rate reduces the expected value of all future jobs. And so current unemployed searching workers are in some sense less picky about what jobs they will accept, and therefore the reservation wage will fall. Okay. Now that we have talked about the comparative static results in this one-sided search model, let me now kind of fill out the rest of this model by trying to describe how the reservation wage property will help us determine something about employment and unemployment dynamics in the long run. So far, the McCall search model has basically just been a model of the reservation wage, W star. And that one endogenous variable summarizes the behavior of individuals in this model by characterizing what wage offers will be accepted or rejected, right? If your exogenous wage pull is higher than the reservation wage, you accept the offer. And you will work at that job until you are exogenously separated. If your exogenous wage pull is less than the reservation wage, you will reject that offer, eat the unemployment benefit, and come back and search the next period. Can we also use this model to help us say something about aggregate employment and unemployment dynamics in the model? We can. Let me illustrate what I'm talking about. Let me define a little bit of new notation here. So U sub t, this is going to be the fraction of agents who are unemployed at date t. In other words, it's the number of agents in the model who are searching and who are pulling from this exogenous wage distribution at date t. 1 minus ut, if we assume that there is a unit measure of agents in this model, is going to be the fraction of agents who are employed at date t. These agents receive a wage W. However, they might be separated from their job in any given future period. Okay, here's the question that I want you guys to think about here. What is the flow of agents into unemployment? That's the first of two questions, really. What is the flow of agents into unemployment? Well, that flow should be equal to the let me restate this question. What is the flow of agents into employment? In other words, what is the rate at which unemployed workers who are searching accept job offers? Well, it would be equal to the fraction of the population that is engaged in search, that is UT, times the fraction of those workers who receive a wage that is above their reservation wage and therefore will accept the wage offer. Well, that probability that the wage is above the reservation wage is 1 minus the cumulative distribution function evaluated at W star. In other words, this is the measure of agents in period T who are unemployed, but who also accept their wage offer. Second question, what is the flow of agents into unemployment? Well, that flow is going to be equal to the fraction of agents in date T who are working, right? So that's 1 minus UT, times the probability that any one of those agents is going to be separated from their job. This product here then represents essentially the proportion of the entire population of mass 1 that will end up losing their job in period T and therefore having to search for a job in the next period. By identifying these two flows of agents into employment and also of agents into unemployment, we can write down the linear law of motion then for the economy's unemployment rate. The unemployment rate, or the fraction of agents at date T plus 1 who are unemployed, is simply going to be all those people who were unemployed in the last period minus the flow of unemployed agents who are now working in period T plus 1. So that would be UT times 1 minus F of W star, plus the fraction of employed agents at date T who lose their job and will therefore be unemployed in the next period, right? So the number of unemployed people is equal to whoever was unemployed last period minus the flows into employment plus the flows into unemployment. Now, some of this cancels. This UT should cancel with this UT, and you're going to end up with UT plus 1 is just equal to, let's see, F of W star minus delta times UT plus a delta. Now that looks nice. Like I said, you'll notice here that this is just a linear law of motion for the economy's rate of unemployment. We can characterize the steady state and the stability of this linear law of motion using techniques that are familiar to us, okay? Hopefully you guys remember from early in the semester when discussing the Solow model that any law of motion that's characterized by just a single variable, so UT in this case, will be stable in the long run around its steady state if the slope of that law of motion is less than 1 in absolute value. Well, the slope of this law of motion is given by F of W star minus delta. Well, we know that delta is a fraction, and we also know that F of W star is just equal to the probability that W is less than or equal to W star, which of course is also a fraction. Well, that implies then that the absolute value of F of W star minus delta has to be less than 1, right? A fraction minus a fraction is either going to be a positive fraction or a negative fraction. So the absolute value of that difference is going to be less than 1. And so the slope of this UT plus 1 law of motion will slice the 45-degree line at a slope of less than 1. And therefore, whatever the steady state is, it should be stable. Now, can we characterize the steady state? Of course we can. It's quite easy to do, right? The steady state is going to occur where U is equal to F of W star minus delta times U plus delta. If we solve this equation for U, we get that the steady state level of unemployment is equal to the separation rate divided by the separation rate plus 1 minus F of W star. Well, that's a positive divided by a positive plus a 1 minus F of W star is also a positive probability. And since we have a delta in the numerator and the denominator, we also see that the steady state rate of unemployment is, of course, between 0 and 1, just as theory should predict. Therefore, the limit as t approaches infinity of ut should be equal to u, and that u satisfies this steady state condition. Now, this steady state should be globally asymptotically stable because the slope of the mapping between ut and ut plus 1 is going to be less than 1 in absolute value, right? Now, to see this, let's just do an example where let's assume for the sake of this argument that F of W minus delta is a positive fraction. Then the ut plus 1 law of motion is going to look something like this, right? Where the intercept is delta and the slope is F of W star minus delta, right? This is the mapping from ut to ut plus 1. The steady state occurs where that mapping crosses the 45-degree line. The steady state value of u occurs right here. Imagine for a moment that u was low, down here at u0. What would u1 be equal to? Well, trace up to the mapping and over, and that gives us U1. Let's project U1 back to the horizontal axis. And it's right there. What would U2 look like? Trace up to the mapping and over, and then project that value back to the horizontal axis, and you get U2. And you see what happens here is that the unemployment rate will rise monotonically toward the steady state in the usual fashion. If the unemployment rate happens to be bigger than the steady state unemployment rate, it will fall monotonically back to the steady state. And so the steady state unemployment rate in this model is globally asymptotically stable. The slope of the mapping is everywhere less than 1 in absolute value. So this model predicts a unique unemployment rate in the steady state and one that is globally asymptotically stable. Now, this particular model is sometimes referred to as what's called a lake pond model. Okay, this provides a little bit more intuition about what's going on and about how unemployment is determined in the steady state. Imagine you have two bodies of water here. A lake, which contains everybody who is, all the fish in this lake are employed, that is 1 minus U. All the fish in the pond, however, are unemployed, okay? There is a tributary here, or a stream, that connects the unemployed pond to the employed lake. The flow of fish through that tributary or stream is given by 1 minus F of W star, right? In other words, that's the probability that your wage draw, if you are unemployed, is going to exceed your reservation wage. If it does, you accept the wage offer and you become part of this employed lake. However, there's also a stream that flows back into the unemployed pond. And the rate at which the fish flow from the lake into the pond, of course, is given by delta. That is the exogenous separation rate. In this model, every single period, there are fish flowing from the unemployed pond into the employed lake, and there are fish flowing from the lake back into the unemployed pond. In a steady state, these two flows have to balance one another so that the size of the lake and the size of the pond stay constant then over time. Those flows will balance when 1 minus F of W star and delta are equal. I'm sorry, I misspoke there. Those flows are the same when delta times 1 minus U is equal to 1 minus F of W star times U. That's in which sense in which the flows are the same, in which case the steady state unemployment rate is going to be constant. Okay, the last thing that I want to do in this lecture then is pick back up this discussion of comparative statics, but I want to continue on our results from before so that we can draw some conclusions about what the comparative static results are with respect to the economy's unemployment rate, right? So in other words, we know how things like the unemployment benefit and the discount rate and the separation rate affect the reservation wage. Can we then draw conclusions about how those same exogenous terms will affect the economy's unemployment rate? Well, let me just quickly at the top of this page write down those key results so that we can reference them when doing our comparative statics here. So the unemployment rate is the separation rate divided by the separation rate plus the job acceptance rate. That is 1 minus F of W star. Right? And this is from, again, from the lake pond model. the reservation wage was characterized by the following equation: B plus A of W star. Where A of W star is equal to 1 over rho plus delta times the integral W star to W bar, 1 minus F of W dW. A prime of W star was equal to negative 1 over rho plus delta times 1 minus F of W star, which is negative. Okay. And I won't write down the comparative static results again, except to say that the partial of W star with respect to B was a positive fraction. You can look on the last page to find the exact value. And the partial of the reservation wage with respect to the discount rate was the same as the partial of the reservation wage with respect to the separation rate, which was less than 0. Okay, this we've done already. First result. What's the partial of the unemployment rate with respect to the unemployment benefit? Now, before we do the math, which is very simple, let's talk about the intuition. Hopefully, you'll understand the result intuitively before you begin the calculations themselves. If we want to think about how an exogenous change affects the amount of unemployment in the economy, then what we need to do is recognize that the unemployment rate is really just a function of the separation rate and the reservation wage. So the unemployment benefit is going to affect the economy's unemployment rate by influencing the reservation wage. Now, what do we know about the relationship between the reservation wage and the unemployment benefit? If the benefit goes up, we already proved that the reservation wage is also going to go up, but less than dollar for dollar. So if a higher unemployment benefit raises the equilibrium reservation wage, what is that going to do then to the flow of agents from unemployment into employment? Well, if it raises the reservation wage, then agents are going to be pickier about which jobs they accept. And so more jobs are going to be rejected, which means that the flow of workers into, out of unemployment into employment is going to shrink. And because that flow shrinks, what you're going to find is that the size of the unemployed pond in this economy is going to grow. So higher unemployment benefits raise reservation wages, which therefore provide a disincentive for workers to accept jobs, and therefore lowers the flow of employment, the flow of workers out of unemployment and into employment. Now we can do the comparative static quite easily, right? What is the partial of U with respect to B? Well, that's just going to be equal to what? Negative delta over delta plus 1 minus F of W star, that whole quantity squared, times negative F prime of W star, so the two negative signs will cancel, times the partial of W star with respect to B. Well, this is a positive over a squared term, so that's a positive, times F prime of W star, that's a positive. Raising the reservation wage will increase the cumulative distribution function, right? Because F is the probability that a wage is less than W star, so that's positive. So this is a positive. This is a positive. And dW dB is also positive. And so you can see here that increasing the unemployment benefit raises the economy's unemployment rate. Again, a higher reservation wage reduces the flow of unemployed agents into employment and therefore grows the size of the unemployed pond in this economy. So contrary to what some people say regarding making unemployment benefits more generous and therefore creating some type of demand effects in the economy, which should lower the unemployment rate, what the McCall one-sided search model says is unambiguously, if we make unemployment benefits more generous, that will provide an incentive for workers to stay unemployed and therefore raise the economy's unemployment rate. How about the partial of the unemployment rate with respect to the discount rate? Again, let's do the intuition first. We already saw that higher discount rates should lower reservation wages. Agents will not be as picky if they discount the future more heavily, and so would be more willing then to take slightly less attractive jobs. So the reservation wage should shrink. Now, if the reservation wage shrinks, then what happens to the flow of workers from unemployment into employment? That flow is going to increase rather than decrease, as in the previous example. More fish flowing from the pond into the lake then is then going to shrink the size of the pond in the long run. So an increase in the discount rate, which lowers the reservation wage, reduces long-term unemployment. A lower reservation wage increases the flow of unemployed agents into employment, therefore lowering the economy's unemployment rate. Again, it is straightforward to do this using comparative statics. It would just be negative delta over delta plus 1 minus f of w star, quantity squared, times f prime of w star times the -1, and so the negatives cancel again, times dw star d rho. So the comparative static looks identical to the one with respect to the unemployment benefit. Positive times a negative, however, makes this whole thing negative. One more, and then we will call it a day. What about the unemployment rate with respect to the separation rate? Now things are a little bit trickier. The reservation wage is influenced by the separation rate in exactly the same way as it is influenced by the discount rate. That comparative static is identical, but the difficulty in computing du d delta emerges because the unemployment rate itself depends directly on the separation rate. So in other words, raising the separation rate not only affects the flow of workers from the unemployed pond into the employed lake by changing the reservation wage, it also directly affects the flow of employed workers into the unemployed pond, of course, by affecting the separation rate. So we're going to have two opposing effects here, right? Increasing the flow of workers from employment into unemployment by increasing the separation rate would have the effect of increasing the number of unemployed people in the economy, right? If more people are getting separated in any given period, the economy's unemployment rate should go higher. However, if there is an increase in the separation rate that lowers the reservation wage, that's going to increase the flow of workers from unemployment into employment. And so the top flow here also increases. Now the question is, which of these two flows increases by more? I think what you're probably going to see here is that there is an ambiguity. We just don't know the magnitude of both of these channels unless we make some more restrictions on the model. So my guess is that we're going to end up with an ambiguous result in this case. Higher separation rates might increase the unemployment rate if the flow from employment to unemployment is bigger than the flow of unemployment into employment via the reservation wage. Well, let's compute this comparative static. It would be the derivative of I'm going to do the product rule here. So the derivative of the top is a 1 divided by the bottom. So that's delta plus 1 minus f of w star minus delta over delta plus 1 minus f of w star squared, chain rule, times the derivative of the bottom, which would be 1 minus f prime of w star times dw star d delta. The first term, 1 over delta plus 1 minus f of w star, that is a positive over a positive fraction plus a positive fraction, so that's a positive, minus a delta over something squared, that's a positive, times a 1 minus f prime dw d delta. Well, let's see, f prime is positive, dw d delta is negative, so this is a positive times a negative, and it's a 1 minus then a positive times a negative, so that's a 1 minus a negative, which makes the whole thing positive and bigger than 1. So we've got a positive minus a positive times a positive. Well, that looks to me like it's ambiguous. Without knowing something more about the size of f prime, for instance, as well as f, you're not going to be able to determine whether the first term is bigger in magnitude than the second term, I don't believe. And again, why is this happening? Higher separation rates increase the flow of workers from employment into unemployment, and therefore that increases the size of the unemployed pond. However, higher separation rates lower the reservation wage, which increases the flow of unemployed workers back into employment, because now more unemployed workers are willing to accept lower reservation wages. So this flow at the top of this lake pond model also gets bigger. Which of these two flows is bigger in terms of their changes with respect to delta is not known with certainty. And so the comparative static should be ambiguous. Okay, that is all I have to say about the McCall one-sided search model. We will pick up in the next lecture and start discussing the Diamond-Mortensen-Pizarriadis two-sided labor search model, in which wages are no longer drawn from an exogenous distribution, but rather searching workers, as well as firms who are posting vacancy, will meet each other according to an exogenous matching function, which depends on the level or the degree of labor market tightness in the economy, which is endogenous to the model. And once a firm and a unemployed worker meet, they will negotiate over an equilibrium wage, not a reservation wage, but an equilibrium wage using a Nash bargaining strategy. More on that in the next class.